gain margin and phase margin. In this lecture, we will see the BOT plot can be used to determine the system stability. Stability of the system can be determined using BOT plot using gain and phase margin. Gain and phase margin on the frequency domain plot are important for analysis and design of control system. The green crossover point is where the magnitude curve crosses at 0 dB, and the phase crossover point is where the phase curve crosses at 180 dB. In order to find the gain margin here, we need to take 180. It will cross at the phase plot here, and at this point we will pull the frequency up until we cross the gain plot here. So from this point to 0 dB, so this range is called the gain margin. For the phase margin here, we will look at the 0 dB here until cross section at the magnitude plot here, go down here until it cross at the phase plot here. So from this point to 180, so this is actually our phase margin. So that is how we get gain margin and phase margin. So this is another example of BOT diagram. So how do we get the phase margin and gain margin? From this example, this is an example of BOT plot. So in order for us to find the gain margin here, so we need to look at the phase margin at 180 degree. Just look at this line and see where the crossover happen at the frequency with the phase plot. So from this line, go to the magnitude, pull it up until you have the crossover at the magnitude plot here. So here until 0 dB here, this one is actually our gain margin. As for our phase margin here, so we need to look it from the 0 dB here until it cross the magnitude plot. From here we go down until you cross over at the phase plot, and then from that point to 180 here, it is actually our phase margin. That is how we find the gain margin and the phase margin of the system. The closed loop system will be stable if the frequency response has a magnitude less than 0 dB. If we see here, if you have 0 dB line in here, okay, so if the gain margin is less than 0 dB, so this is our 0 dB here, okay, so it is less than 0 dB, so the system is stable. And if the phase margin value is greater than 180, okay, going to up here until this is 0, so the system is stable. So for how do we indicate that the system is unstable or stable? So as mentioned previously, if the gain margin is below 0 dB here, so this is a stable system. If the phase is greater than 180 here, so the system is stable. However, if the gain margin, if we got here and then going up, and the crossover at 0 here and at the magnitude here is actually greater than 0 dB. Oops, should be less than 0 dB. Then the system is not stable. And how about the phase margin? If we pull 0 dB here, down here, so the cross section should be somewhere here. Whatever is okay. So let's like your graph something like this. So pull down here, and that is actually your 180 is here. Okay, and then you can see that, oops, what happened? Phase margin is below 180. It should be going up, so meaning the system is not stable. So what to do? So you need to design the system or play around with the gain of the system. So depends on your design. Okay, that is how you analyze a system using board plot. That's website. So you can see this exercise on body plot or board plot. So this is example that I've shown in the slide previously. So how do we go to the MathsWorks website? This is an example that I showed in the slide previously. So in this website you can find several examples of board plot. So here we will try to plot our board plot using MATLAB. So let's try this example. If you do not have MATLAB, you can just try to click this example and it will run online. So before that, let's look at this example. In this example, it asks you to plot gain and phase margin of a transfer function. So for this example, create a continuous transfer function here. So this is actually transfer function represented in a MATLAB code. So this is actually the transfer function written up here. So if we are using this margin, it will display the board diagram with the phase margin and gain margin of the system. So you can see that in this plot. So we look at the minus 180. So see where does it cross here and going up here. So this is actually from 0 to this point is our gain margin. So the system is stable. So from 0 until the magnitude plot come down here, and then at this point, so we can see, oh, this is actually our phase margin. So it is greater than 180. The system is stable. Okay. So let's try this example. So we have something like here. So for this example, we need to create the continuous transfer function here. Okay, so it is there. So and then it display the gain margin and phase margin of this transfer function. So we run it. Okay. The system will plot directly your phase margin and gain margin. So you can see that the system already give you the value of your gain margin 6.02 dB at 1 radian per second, and your phase margin is equal to 21.4 degree at 0.682 radian per second. So as easy as that. Hope this will help you. Okay, how about we try the second example of transfer function. Okay, this is the transfer function that we would like to test. So this is a discrete transfer function. Okay, to see, so using the margin, okay, system, so we can see that when we plot this transfer function, we can see directly looking at this. So this is minus 180 when we put it here, okay, until here, and then put it up here. So we can see that the gain margin is at 6.24 dB. So when we look at the phase margin, we look at 0 dB and it's coming down here. Oops, so we can see that, oh, the value is minus 180, and this one, it should be stable.